So as I was saying, today we're going to talk about water quality measurements. This is going to be quite a in-depth session in which we were going to talk about a lot of things. We will talk about the metrics of the sensors and the sensors that we're using, how to calibrate them, how to deploy them, how to maintain them, and properly even clean the sensors. And we're going to need a lot of things for this session. So ideally, all of you should have a water station with different parameters that are able to measure different things. You'll also have calibration solutions, and these are standard calibration solutions that come with the sensors that allow us to establish the ranges or the calibration points for each of them. Some of you would also have replacement solutions in case that it applies for the probe. Cable seals, this is the important topic regarding how to waterproof cables, especially for those that have long cables and that are a little bit delicate and not waterproof. You will need the same setup as we used last time or in the previous sessions with Victor, in which you connected to the sensors via your computer. So you need a computer, an Arduino IDE, or a similar terminal software, a USB cable, and then some additional laboratory things like distilled water. And finally, a file or a tool. We will see this that for some of the sensors is necessary because you need to sand and let's say clean the sensors with a file. So let's go. Let's start talking about water sensors. So first, we're going to try to understand a little bit what we are measuring and what the water station is able to do. So the water sensors that we support are mainly what we call physicochemical parameters. So they are able to measure physical chemical characteristics of liquids. In particular, we'll be measuring water, either fresh water or seawater. And ideally, a complete station will be able to measure pH, dissolved oxygen, electric conductivity, temperature, and the oxidation reduction potential, or ORP, as we call it for short. In some other units, there's also a GPS for mobile measurements, but this doesn't fall into the realm of physical chemical parameters for liquid substances. And this is ideally what we can support. We will see different particularities on what these things mean for this particular case, but we are not able to support any, let's say, more complex bio measurements like nitrates, phosphorus, biofuels, and things like this. We are limited to this type of sensors, mostly because the availability in terms of cost and support, which it's currently and not probably in the state of the art of low-cost sensors currently very well supported. Just a couple of notes about these water sensors. The first one is that there's extra material along with the presentations that we won't dig into, but we think that is very valuable. In particular, there are some citizen guides and documents by the US government and national protection agencies and other environmental agencies in general that provide very good documentation. And also, you will see that a lot of this material comes from various sources, but one in particular is the Atlas Scientific sources, which is the manufacturer of the water sensors. And we, as a smart citizen, integrate them into our platform. Just note that they have very good documentation, and please refer to the datasheet in case that you are lacking information on our probes. And of course, you have the datasheets also included in the presentation, and of course in the documentation of the project. So starting to talk about different metrics. First of all, what is the first sensor that we're going to talk about is pH. So the pH is basically concentration of hydrogen ions in liquid. It ranges from 0 to 14. 7 is what we call a neutral pH, and lower than 7 are acidic, higher than 7 are basic. The importance of pH is that it limits the solubility of different chemical substances and the availability in terms of biological activity for those substances. So it means that it doesn't only determine if you can dissolve, for instance, phosphorus or nitrates that are very important for biological activity, but it also determines whether or not they are available for that life, let's say. It also can affect the composition of water in terms of other materials like heavy metals like lead, copper, that of course can be very toxic at high concentrations. In this regard, it's also related, and we will see this all throughout the presentation, that is very cross-related with other metrics for all the physical parameter metrics we're going to be talking about. And in this case, it's very important for solubility of phosphorus and the nitrates, as I was mentioning. And it also impacts plant growth and can lead to high dissolved oxygen demands, which means that we can create environments in which we have very high dissolved oxygen demands and then have what is called anoxic environments in which we lose oxygen because it's a lot of consumption, and we create dead zones in water. In seawater, you know that in MINKE project, we are talking about marine environment. So we talk a lot about seawater in general. So pH is very important in the what we call oceanic carbon cycles, which is reactions that are happening in the water that happen because of the change with the atmosphere and the activity of the different components in water. And there's an important aspect, which is the ocean acidification, which we have seen the pH becoming more acidic in the oceans as they have been absorbing a lot of CO2 due to industrial activity in the recent years. And this has happened, again, as a consequence of the increased CO2 concentrations in the air provoked by human activity. And then, for instance, this creates more problems, for instance, for small marine organisms to trap CO2 when they build their shells. There's less coral, and then there's less food as the acidification of the water, it's corrosive to these shells. It is important as well to highlight that this is a very important metric, and the ocean acidification is endangering a lot of species, and especially the survival of phytoplankton that then are related to many other things, as and one of them is the capacity of the ocean as a CO2 trap. So the ocean, as it becomes more acidic, it cannot absorb as much CO2 as it does now. What do we do to measure pH? So we will use a probe that looks as in the picture. It's a very delicate probe, and you can see that it has this bubble, this glass bubble on the top that is super delicate and that can get damaged. So please handle it with care. You will see that it's stored in a soaking bottle that has to be removed. We'll see that later on. And in terms of performance, the range that is able to measure, it goes from 1 to 13. So it's not covering the full pH range. In this case, it can be submerged up to 35 meters. And this is because this glass bubble that we have to protect, it takes at around 4 seconds to respond, and it's safe to use in general. Important is to consider that the sensor needs a very simple preparation. It needs to be calibrated. We will see how often, and it needs to be maintained. Especially, it has to be maintained for cleaning, because all these crevices will accumulate dirt and biofouling, and it will be necessary to maintain and clean it, as we will see later on. Normally, we also suggest that the sensors should be used in a continuous manner, but in case that you are taking samples, for instance, you are collecting a sample and then measuring it, we suggest that you measure very quickly, because the pH of the water can change very fast, as it depends on the chemical activity, and that chemical activity can evolve very fast. So either you take continuous measurements or you take the sample on site and then measure on site. If you take the sample and bring it to the laboratory, it's going to be very likely that it's not related to the actual sample that you wanted to collect on site. Moving on to other metrics. In this particular one, we're going to talk about dissolved oxygen. So dissolved oxygen, it's it's a metric of how much oxygen is dissolved in the water and also available for living organisms. It's normally affected by the movement of water. So, for instance, aeration and other changes with the atmosphere, either by movement or by high splashes and things like this, will provoke aeration in the water and then create or lead to a higher dissolved oxygen value. And it's important as well because it's a consequence of the photosynthesis of aquatic plants. So aquatic plants also generate oxygen as a consequence, the same way that terrestrial plants do. And it is essential for aquatic life. So here on the right side, you see, let's say, a minimum concentration of dissolved oxygen that is necessary for living organisms to survive. And you see that on the very bottom, we have, for instance, mosquito larvae that are able to live in very low concentrations of oxygen, and then salmon and other ones that kind of make sense when you see these these waterfalls and salmon living in those areas. Important relationship with temperature. So the higher the temperature, the lower the dissolved oxygen, and vice versa. And in seawater, it is important to consider dissolved oxygen because normally living things have a lot of inertia, and they are, let's say, acclimatized to a certain percentage of oxygen. So the lower the dissolved oxygen or fluctuations in this case will create devastating effects. And we are creating a lot of what we call dead zones that are called hypoxic, which means areas that are lacking oxygen. And this is again due to warming temperatures and particularly differences in concentration along with human activity and proliferation of plants that create what are known today to be more than 400 dead zones in the ocean. This is again related also to pH levels and temperature, and just consider the ocean also as a very complex system, and that we are considering here a very small hint into what we are trying to assess with these sensors. How do we measure dissolved oxygen? So we use this galvanic probe. This is again manufactured by Atlas Scientific. It has a very decent range and can be submerged down to 70 meters. The probe is measuring dissolved oxygen by reacting with the water. So a stagnant water or non-moving water will not react properly with the probe, and you need to move the probe a little bit so that it reacts and provokes the small currents around the sensor. we will see that the sensor depletes over time this capacity to react with the oxygen dissolved in water, and that is also very delicate. And we will see in the maintenance section how to take care of this. This sensor is not very complex to prepare, but it's a little complex to calibrate and to maintain. Don't be scared, because this is it's fine, but you will see that it takes a little time, and there are quite a few particularities for calibration and maintenance. And in case, the same as we discussed with the pH sensor, in case that you're taking samples on site, you have to be very careful and very methodic, because dissolved oxygen evolves almost immediately. So if you are taking a sample on site and not using the sensor by simply deploying it and take continuous measurements, you will have to be very careful of not trapping bubbles in your in the container that you are taking the sample in, and also to take considerations whether with respect to where you take the sample. So please check the documentation for further information, and also the guides that I mentioned earlier, because they specify very good details about how to take dissolved oxygen samples as well.